Uh, the mic is on or not? I can't hear anything.
Hello. Hello.
Yes, now I can hear.
Okay. Uh, Hi, this is Shruti, and you are Dr. Robinson. Why are you taking this course,
Uh,
by the way?
Actually, I teach my undergraduate, sorry, my postgraduate students quantum mechanics. So I thought I will extend my journey to symmetry also. Only for UG students only, I am teaching this course. So since it is the same instructor, Anindya Datta, so I thought why I will join this course also. So the
Okay.
initial part was little bit okay for me. So I thought, okay, I will continue along with my students. So quantum mechanics, my students also have joined. So together we are attending the course. For group theory, it comes only in the next semester. So only I have joined the course now.
Okay, got it. Okay, where do you teach, sir?
I teach in Christ College, Irinjalakuda.
Okay, okay, fine. Hi, my name is Shruti. I'm PhD student, and
Okay.
I'm the TA for this course. And in
Mhm.
this live sessions, I'm just discussing the assignments for the
Yes.
students. They are supposed to do the assignments beforehand, and I'll just discuss them for like they can check whether they have done it correctly or not.
Okay. Okay. Yeah. I am
So
used with the NPTEL courses. So I think we can. I think only myself has joined. Nobody is there. Right?
yes, generally people do not join because they watch the maybe the YouTube video or the recording.
Okay.
That's right. Okay. So you know everything, right? Or like you have read the course.
Yeah, yeah, I have gone through the course up to week two. Week three, I have not gone. Uh, Among the assignment, I was trying to do it today. And the second question, I had some doubts. Second one.
This one.
Yeah, this one.
Okay. Let me
So, what is the
just.
normal procedure? So, you will be doing all the, you will be
Yeah, I'm
solving all the
supposed.
assignment?
Yes, I'm supposed
Yeah.
to solve all the like most of the questions.
Because
If the
it should be recorded, right? For the
yes,
recorded session. Okay,
yes,
okay,
yes.
then you can start. I will be there.
Okay, fine. So in the course, this question has actually been taught in the course transformation matrix for clockwise rotation in
Yeah.
along this direction x y
Okay.
z with an angle any angle theta.
Yeah.
So for students actually I'll be teaching generally, okay, if don't mind.
Yeah, yeah, I don't know.
So for any uh, axis rotation along any axis, suppose cn by it can be c1 c2 c3 likewise n can be anything, so depending on the n we will have the degree of rotation 360 by n. Now
Mhm.
how every time in the last sessions we have seen that we were checking the how the molecule changes its configuration by actually rotating the molecule, but for larger molecules with many atoms we cannot do so, right? So we need to have a system to do the transformation to check whether we are getting an equivalent configuration or not, or whether the symmetry element is present in the molecule or not without actually rotating the molecule. So for that mathematical concept we use these matrices. For every symmetry operation we have a matrix associated with it. for every symmetry element we have a matrix associated with it. So when we apply that matrix on the molecule or and a bond like that, we can either rotate it or reflect it, and we can see whether we are getting something similar to the actual configuration or not. So for rotation, suppose now for applying this matrix we need two things, right? Suppose generally we will have some matrix 2 3 4 5, and we need another matrix. So this is matrix A, this is matrix B 1 and 2, suppose. Then only we can do this multiplication, right? And the order should also match. So if this is n cross m, it should be m cross k. Now, so this one, suppose this one is our transformation matrix. This is what we don't know, right? This matrix can define either a bond or maybe an atom, anything, or maybe the whole molecule, atom, or maybe in some cases it can be orbitals. So this, the second matrix is called the basis matrix. Based on the basis, your answer will change. The transformation which you will get, this is called your transformed vector. what what is the resultant will be the transformed vector or transformed matrix. So your, this one is your initial configuration, basis is your initial configuration, and this one is your final configuration. So if these two things matches, then we say that yes, this symmetry operation exists in this molecule. So we need to get a equivalent configuration without actually doing the all the rotation and reflection on pen and paper like that. We can do the maths and we can know whether it is present there in the molecule or not.
Okay.
So if now I will suppose I give an example whether now if you don't need to change anything, if this is your basis xyz and you need to get the same thing xyz, what should be the transformation matrix here? This is simply like whether we are multiplying an element. Now remember we have talked about group theory, like mathematical group theory, whether every element in the set has its identity element, which when operated with the element reproduces that element. So if this element is associated with its identity. Now how identity gets transformed to matrices, you must have learned about identity matrices, right? Where the diagonal elements are 1 and off diagonal elements are 0. So this is a 2 cross 2 identity element. Now which whatever order we will use here depend upon the number of elements in the basis set. So here I cannot use 2 cross 2 because I cannot do the matrix multiplication. So here I will use a identity element of order 3. So if I multiply this, I will get my basis as it is. So this is the actual meaning when we say we are applying an identity element on a molecule. We say that it doesn't change it, but we are actually doing some operation which with that. Right? This is first. Now, so the
Yeah.
question is actually about rotation. So let me come to it later. Then next operation is what? Uh, Reflection. So these are the easier ones. So let me discuss this first. Now, in reflection, suppose you have some imaginary molecule like this, okay, and you apply a plane like this. Okay, so this plane is, so this one is sigma y z. Then what this plane will do, actually, so it reflects 180-degree, right? So this will come here and this will go here. The atoms will get swapped, right? So suppose
Yes.
in the coordinate system, suppose this atom had coordinates x1, y1, z1, and this had x2, y2, z2. So now f has become x2 dash, y2 dash, z2 dash, and this has become x1 dash, y1 dash, z1 dash, right? They have in, we can say they have swapped their positions, but they have got new coordinates. Now, how do we know what are these actual coordinates? Because simply here you can say that this is a simple case, right? Here you can say they have changed their y positions without changing, uh, sorry, they have changed their x positions without changing y and z. But for complex cases, you cannot, with some, when it comes with some angle, you cannot say that. So for that, we need to have another matrix. So here you see, if the plane is, if the plane is xy plane, the atoms on the x and y direction will remain same, or the x or y coordinate will remain same upon reflection, and z becomes minus z. Suppose in this case we had the plane y and z, so y remains y, z coordinate remains z coordinate, but x becomes minus x, as you can see here. So they have simply changed this position, this coordinate, which is the x coordinate. There is no change in y or z direction. So when this is the simple case for reflection. When you are performing any reflection operation, if the plane is yz, if the plane is xy, z will change. If the plane is yz, x will change. And if it is xz, y will get transformed to minus y. Now here, because the reflection does, we have 180-degree reflection. Here we are not mixing any coordinates. So x is not becoming y. X is not becoming y, or z is not becoming x. So the coordinates are not getting mixed in this case. This thing will happen when you rotate the molecule. Upon rotation. Okay. So reflection is a simple case. Upon reflection, so based on this, we can write the transformation matrix for reflection. So what if now suppose I'm writing for sigma xy, then what should change? This is the transformed matrix. And this is the basis set. So from the basis set, if I apply a sigma y xy plane, then the coordinates of only, if it is xy, only z will change to minus z, and x and y will remain same. Okay. Now can you guess what kind of matrix we can apply here? So you have seen the identity one here, identity. If it is 1 1 1, then it gets transformed to xyz. Now if I change this one to minus 1, then this z will become minus z, right? So here you just need to have 1 1 and minus 1 in this column, others will be 0. Now why here the off diagonal elements are 0? Because we are not mixing any coordinates. When you will have the mixing of the coordinates, these off diagonal elements will not remain 0 anymore. We will have some value there. Now this one is your transformation matrix for reflection, and reflection through a particular plane which is x and y, because based on this only you can see it is changing the z coordinate, so it is an xy plane. Similarly you can write one for sigma yz and sigma xz. So in the yz, x will change, the other coordinates will remain as it is, and the off diagonal elements will be 0. And similarly sigma xz, so y coordinate will change, others will be same. So this was the case for reflection. But now in case of rotation, because rotation can happen by any angle theta. So if the rotation happens with an angle 180 degree, it will be something similar like reflection. But if there is any other angle theta, then the case becomes complex. But let us first see the simpler cases. So if in case of rotation, suppose this is some, okay, this is some random molecule with this kind of geometry, and I want to apply a C2x. Now again the direction notation is same. So the C2x will be something like this in this direction, and it will rotate it like this. So in this case, since these are atoms, what will be the change? So the transform matrix will look like this. This has gone here and this has gone here. But the and this is not a tetrahedral molecule. I'm just drawing a planar molecule with bonds in the random direction. Okay, so if you see, if you can notice that these bonds which are on the axis of the rotation, they have not changed their place, like these R, C and P, but the atoms or the bonds which are off axis, they have changed their places, they have changed their coordinates, so their coordinates have transformed. Okay, so here this is simply opposite to the reflection thing. If you are applying any rotation in the x direction, so x will remain same, y and z will become minus y and minus z. Okay, if the reflection, if it is 180-degree reflection, C2, if you are applying C2y, then y remains y, x and z becomes minus x minus z, likewise. Okay, but if you are doing a rotation by Cn and any direction, suppose z, n will decide the angle, so the angle can be, theta will be 360 by n, right? And z is the direction. So in this case the matrix looks like, so since the direction is z direction, z coordinate is not supposed to change, like in these cases. So if it is y, the y does not change. If it is x, x does not change. So here if it is z direction, z coordinate will not change, it will be 1, and the other coordinates will change. How much? By an angle. This is a formula, cos theta minus sine theta, here sine theta cos theta. Now how do we get this formula? Here in these cases it was simple, right? But here now we have, since there is the mixing of these coordinates, x can be a combination of x and y can be a combination of again x and y. So y, x dash and y dash. The new transformed coordinate x dash can be a combination of both x and y. So here we have, in the off diagonal elements, we have some values, and since z is the direction of the rotation, so the z ones are not changing. There is no mixing of coordinates in this, in these two directions. The mixing is only happening in here, x and y, right? Now
So the present matrix which you have wrote is for clockwise direction or by taking anti-clockwise?
it is for anti-clockwise, but the clockwise or anti-clockwise, only the signs will change.
Yes, yes. Okay.
suppose, so the question was about y-axis rotation. So let us now come to that. Based on what is our matrix system, this is x, this is z. So here we are getting transformation in the y direction. Now let us suppose if you have some original maybe some bond which is in this direction, and it has coordinates x1 z1, and it has it has been rotated by an angle theta c n y. Theta is again 360 by n. It has been rotated by an angle theta which transforms it to a new coordinate like this, which is x2 z2. Now this complete angle is theta. Okay. Now we are actually deriving how do we get to that transformation matrix. So let us put some projections here. This distance will be, suppose this distance, the length of this vector is L. This angle is alpha, and this angle will be theta minus alpha. So this distance will be L cos alpha, and here this will be L sin alpha. Now upon transformation, we have, this is minus of z2, this one is, this distance will be, how much is this angle? Theta minus alpha. So this one will be sine theta minus alpha, and this one will be L cos theta minus alpha. Okay. So from these you see x1, this distance x1 is equals to L cos alpha, z1 is equals to L sin alpha, x2 is equals to L cos, this one L cos theta minus alpha. Now if you remember those trigonometric formula, cos theta minus cos alpha can be expressed as cos theta cos alpha plus sin theta sin alpha, and similarly sin theta minus sin alpha can be expressed as sin theta cos alpha minus cos theta sin alpha, right? So we can write x2, which was, we can express this using the formula. It will be L cos theta cos alpha plus L sin theta sin alpha, right? This is x2. Now if you can see any similarity, L cos alpha is x1, L cos alpha is x1 and L sin alpha is
y1.
x1 z1. So therefore we have, now here you see x2, which is the transformed coordinate, is getting expressed as a sum of the both the coordinates, the original coordinates. So it is mixing of coordinates. Right? Similarly, you can do for minus z2 is L sine theta minus alpha. This one minus z2. Sine theta cos alpha, and this will be sine alpha cos theta. Okay, so again go back to what we have earlier. L cos theta is x1 and L sine alpha is z1. So you can write this as minus x1 sine theta plus z1 cos theta, and y2 remains as y1. There is no change. So we have now three transformed coordinates. Transformed coordinates written as a combination of original coordinates. So y2 is y2. Because the rotation is happening along the y direction, there will be no change in the y coordinates. Z2 can be written as Z1 cos theta minus x1 sin theta. Okay, so now we have got this matrix. Originally we had x1, y1, z1. Then we have got x2, y2, z2, which is the transformed coordinate. Now along the y direction there is no change, so y atom, it will be 1. Along the y direction there is no change. Now this will be cos theta. As you can see here, if you multiply this and this, you will get this, plus this and this will be 0. This here it has to be sin theta. So you get x2. Similarly, this one, in case of x, it will be minus sin theta, and in case of c, it will be cos theta. So likewise, we get the transformation matrices. This one is now for c to y along the direction clockwise. For the anti-clockwise, you can change the signs. Okay. Now let us come to the second question. Okay, this your doubt, right?
Yes.
Now we have three oxygen atoms designated 1, 2, and 3. This is an oxygen, this. The C atom is designated as 4. So it is like this. These are oxygen atoms, and since these are the p orbitals, I am showing it like this. So it will have positive and negative lobes. Suppose I am putting a darker shade on one, so you can think that this is, suppose this has a positive sign, this has a negative sign, and the whole thing has a -1 charge, CO3 minus. Now, taking the pz orbitals, the three oxygen atoms are labeled as the bases. Now here, so what I told earlier, that the basis set, here the basis set can be a bond, can be an atom, or can be the orbitals as well. Okay, so here the question is asking us to take the p orbital as the basis set. So we have to transform the p orbitals here. And the transformation matrix is this. It has given the transformation matrix. We need to identify which operation is that. Now, let us, here we need to do it one by one. For suppose it is written C3C, means rotation by C3 means rotation by 360 by 3, which is 120, along the Z direction. The direction has also been mentioned. This is X, this is Y, and this above the plane is Z direction. So if you do that transformation, how will it look? Let me write it here again. This is one. So they have given the nomenclature 1. So this will be PZ1. PZ2. This is PZ3. Now if you do a C3 along the Z direction, suppose clockwise, then what you will change? This will come here, this will go there, because we are doing along the Z direction. So here instead of 1 you will have 2, P2, 1 will be here. Now you see the lobes are not getting changed. Positive and negative lobes are not getting changed because we are rotating, uh, through Z direction. We are not flipping it. If you will do a rotation along the X direction, then it will change. This is 1. This is PZ3, right? So we have changed the molecules like this based on C3 operation. So now see the original coordinates and the transformed coordinates. What has happened? PZ1 has become PZ2, PZ2 has become PZ3, and PZ3 has become PZ1, right? So there is a
Yes.
cyclic rotation, 1, 2, and now the transformation matrix should look like 1. Now we know this, what has changed to what? 1 has changed to 2, so PZ2. 2 has changed to 3, PZ3, and this is 1. Now, based on this, what numbers will you put here so that the actual answer is like this? So for that, let me first write. This is 1, 2, 3. Here 1, 2, 3. 3 rows, 3 columns. Okay. So first has become second. So first and second, here it should be 1. Because the first, when you will operate it like this, the others will remain 0. So when you will operate this multiplied by this multiplied by this, and this multiplied by this. So 1 has to get transformed to 2. So here there should be a 1 in this case, in this place, right? So this value will be 1. Likewise, 2 has get transformed to 3. So in the third place, we will have a number 1. And others will be 0 because those has to vanish. And here we will have 1 in this place, others will be 0. So this is the transformation matrix for this basis set for this symmetry operation C3Z. If you change the direction, the transformation matrix will change. So here we have been given the matrix 1 here, 1 here, and 1 here. Is this same? No, this one is not same.
Mhm.
So based, you can guess what it will change. So PZ1 has to become PZ2 because there is a 1 in this place. 2 has to become 1. PZ2 has to become PZ1, and 3 remains 3. PZ3 remains PZ3.
So it should be a reflection, right?
It should be a reflection. So which reflection? Along Z.
Along C, yeah.
In the reflection, yes, the Z axis should be in the,
Unchanged. Yeah. Plane
yes,
should be X, right? Yeah. Okay.
plane should be XY, and the Z axis will remain unchanged. So I think
Okay.
it should be this one.
Yes. Yes. Okay.
But if you want to go through, if you can check for C2Y. But in case of Y, in case of rotation, you need to change two coordinates only. uh, Sorry, in case of yes,
Rotation, I think all the coordinates will change.
in case of any rotation, because this is in case of this rotation, uh, all everything should change, because even if you rotate the orbital so here it is an orbital, it's not an atom. So the even if you rotate along the y-axis, the signs will flip. So these along we have, along y-axis we have 3, right? So pz3 will get transformed to minus pz3. The signs will change, so there you will have a -1. In case of, in the transformation matrix, 3 cross 3 element will be a -1.
Mhm.
plane YZ. So YZ will be this plane. So in that case, this will not change. Y will not change. There will be no change in the sign as well. And this will flip. This will get changed to this will get changed to. So PZ3. I think the answer is fourth one. So YZ plane will be like this. 3 will not get changed. And the XY. So for reflection, we will have no change along the direction of the plane. It is YZ plane, so there is a change in the X, right? So here there is no change in the X. Okay, yes, correct. This is the answer. XY, sigma HXY. No. Sigma HXY. H means what? This is a molecular plane. Let me get you through. So this is PZ3. This is PZ1. This is PZ2. And this is the molecule. If you do a molecular plane, sigma H is what? Sigma H is molecular plane. So the plane, what this is tricky. So this plane is like this.
Plane is XZ plane, right?
Yes. So it contains all the atoms, all three oxygen atoms and the carbon atom is on the plane. So when you will do that reflection, all these orbitals will become like this. So the answer is the last one, not this one. The molecular plane will not change the position of the atoms in this case, but it will just flip the orbitals, the lobes of the orbitals. Positive will become negative and negative will become positive. So molecular plane will not be the correct answer. Now if you apply 1. This plane is like this. That plane is y and z. Like this. It contains this bond. This bond is there on the plane. So these two will flip and this will remain as it is. Okay. So let me erase this. The correct one is this one. For the same figure as in the previous question, the transformation matrix for S3Z. Now, S3 along Z direction is a combination of, this is improper axis of rotation, which is a combination of rotation followed by a perpendicular reflection. So you are rotating along the Z direction, the reflection plane will be YZ. Now, for rotation along Z direction, so what will happen? So if you, this is the Z direction on top. Now again there is a cyclic rotation. For one will come in place of two will come in place of one, likewise, right? So the transformation matrix will be 1 becomes 3, 2 becomes 1, and 3 becomes 2. Again the perpendicular reflection, so this is now like the xy plane, the molecular plane. Okay, so as I told earlier that when you are applying the molecular plane, since it is, we are, the basis set is the p orbital, not an atom, the p orbital, the lobes will flip the sign. So here it will be, upon applying this reflection on the yz, all the signs will change, right? Because the pz1 will become minus pz1. Okay, so when you are multiplying this, you will get something like this. Here it is a 0. So I think this one should be the answer.
Shruti, I think maybe according to the convention, you have to write first C3, right? Then
No, no, no.
first,
We can apply sigma also first,
okay,
because it is what I told earlier, that the order of application does not matter.
yeah, okay,
Because here in this case, or in any other case, if the order of the matrix will not change, so if you do this here and the other way, it will not matter,
okay.
here or here, in the multiplication product will not change, right? So so uh, are you clear in this question?
Yes, yes,
These two
it was
questions,
fun.
these are similar. Okay, now coming to the next one. For a D2H molecule, consider the principal axis along the z direction using the unit vectors along the three Cartesian axes as the basis. So we need to pay attention on what we are taking as the basis. Unit vectors along the Cartesian axis. The resultant symmetry operation for this is, now let us suppose you have a D2H molecule. So how will it look like? So it has a molecular plane perpendicular to the D2H, means it has a plane perpendicular to the principal axis. So suppose this is, and it is a D2, not D4. So I will change these atoms to this. So if this is 1, this is 2, this is 1, this is 2. So this kind of molecule will have D2, will have a molecular plane, and the principal axis is the z axis. On top of this plane of screen will you have the z axis, planar kind of molecule. Now if you apply sigma xy, what will happen? There will be no change, since sigma xy is the molecular plane, and in this case we are not considering the orbitals, we are considering the unit vectors, or you can say you are considering the bonds as it is. So when you apply sigma xy, there is no change, this simply remains like this. Had it been the p orbitals like in the previous case, sigma xy would have changed the, flipped the lobes. So there would have been a negative sign there. But now here the basis set is not the p orbitals but these bonds itself. So there is no change in the signs of these bonds. Now, then we have to apply C2X. So C2 will be, now this is the X direction, this is the Y direction. So C2X will be in this direction. Here what will happen? The atoms on the rotational axis will not change its place, but the other atoms will get flipped, right? Now this operation is similar to what? C2Z. So suppose if you apply C2Z, C2Z, let us see. It will be like this. So C2 means 180-degree rotation. In that case, C2Z. In that case, this will be M1, this will be M2, this will be N2, and this will be N1. Understood? So now these two are not similar, so this is not the answer. C2Y. If you apply C2Y, just choose a different color. C2Y will be in this direction. In that case, you will have M2, M1. These will be unchanged. Okay. Now this also is not same. This also is not same. So we have discarded the first two options. Sigma YZ. A M12. This is X, this is Y, this is Z. YZ is this plane. Right? This is sigma YZ. So now again the bonds or the atoms on the plane will not change its place. N1, N2, this will be M2, this will be M1. Now this also is not same as, this is same. We have M2 this side and M1. Or did I write it opposite? M2, M1. Okay, correct. M2, M1 this side. So now this also is not same as that one. Then the last option must be true. That is sigma ZX will be this plane. this will be N2. M1, M2, N1, N2. Yeah, now this is same as what we got after this multiplication. Right? So like this we can check these. A cyclic group among the following. Cyclic group. So suppose suppose the first operation is x. The next operation is x square and another operation is x3. Okay, then so here, let me first tell the answer. Here the answer is C3. Now what I'm trying to tell is a group is called a cyclic group if you repeatedly do the operation and that element already exists in the group. Suppose in C3 the elements which exist in C3 group is E, C3 and C3 inverse. Okay, so here your x is C3. X square, when you do x square means C3, applying C3 two times, C3 twice, which is same as C3 inverse, and this all is already a part of the group. Then when you apply the operation three times, which is C3 3, and CNN is always identity, and this also is the part of the group. So this kind of group is called cyclic group. When you apply the operation multiple times and the resultant symmetry operation is already a part of the group, then those kind of groups are called cyclic groups. And suppose C22 means you applied C2 once and then you again applied C2. So C2 once gives you 180-degree rotation and another C2 will give you another 180-degree rotation, which is 360. So this is same as applying the identity element. Uh, do you have doubt in this question? I think this has already been taught exactly as it is in the class. Just looking.
Yes, these questions are okay.
Yeah, I'm just looking at the class notes whether think I've read these classes years back, so I forgot what has exactly been taught, but I remember that this is a theorem.
The second option will be the right answer.
Yes, 1 by. Okay, I think this is enough. A and B is the inverse of. This is simple, right? You can do it.
Yeah. Yes, yes, yes. I had confusion with that second question because I never thought about that p orbital signs will change upon rotation.
Yeah. This kind of question comes in these exams, this CSIR exams and
Okay, okay,
P orbitals. This is a good question, I think. Yeah.
okay.
So I think I'm done with this because these only were the last three questions are not so important. They have already
Yes,
been
yes.
taught in the class.
Yeah. Okay. Thank you.
Yeah. Okay. Are you watching all the lectures?
Yes, yes.
Okay. Nice.
My one student was there. I think he just completed PhD and he's doing some research assistant. I think
Where?
Vishnu, Bombay IIT.
Okay. Nice. Which department?
He was in energy department. I think he was Vishnu Lal.
Okay. Nice. I don't know personally, but I'm in the chemistry department.
Okay, he was in the energy. He was for that integrated PhD course. That one.
Yes, yes. Energy department offers that.
Yeah.
That is a good course and good choice. You can get
Yeah.
it done. Masters and PhD both. Okay, so
Okay.
shall I
Thank
close
you.
this
Thank you,
session?
Sudhi.
Yeah.
Yeah. Sure.
Okay.
Thank you. Bye.
Yeah. Thank you for joining.
Bye.